So I'm going to talk a little bit about, as Guy mentioned, the global energy challenge. Will we ever stop using fossil fuels? Which we did choose that title to be a little provocative. So I'm much more comfortable with numbers and charts and figures, but off there, as my wife continually tells me, there are visual learners too. And this picture, I think, really encapsulates what I think about as being the global energy challenge. And in my version of that, there are really three goals, and all those goals are captured in this picture. And so what you can see in the picture, oh goodness, there it is, yeah, is we have a guy riding a bike in Beijing. And what I consider to be the first leg of the stool of the global energy challenge is how do we get access to inexpensive and reliable sources of energy that are so critical for economic growth. And you can see, and anyone who's been to China will recognize, like you can feel the motion, you can feel the action. And you know that is driven by energy. And actually, in this case, it's largely driven by fossil fuels. So that's the first leg of the stool. The second leg of the stool is immediately apparent as well, and that's, you know, this picture is in the middle of the day in Beijing, and yet you can't see the sun. And our guy on the bike here has on goggles, and he has on a face mask, and he's very, he's very aware that there are a series of, you can tell, a series of health problems associated with the use of the energy that is fueling this economic growth. And then the third leg of the stool is not immediately visible, but everyone kind of knows it's there once you see the pollution, which is coming from the fossil fuels, and that's climate change. And the same fossil fuels that are powering that growth that are also causing air pollution are also causing climate change. And so what I see as a challenge is how do you try to navigate between those three goals? It's not that hard to think of policies or actions or ways to design society that achieve one of them, and sometimes two, but it can be very complicated to think of something that hits all three. And so with that setup, I'm going to talk about 7 facts that I think explain the difficult balance that we face between energy and growth. And so number one is, you know, some of these facts are practically obvious, but energy is critical for growth. And here, you know, data is so infrequently gives you something reliable. It's usually a mass of points. But here, what you can see on the x-axis is there's log GDP per capita, and on the y-axis is a measure of total energy consumption. And you can, these are all, each data point is a country around the world, and you can see there's an extraordinarily tight relationship. And there's the U.S. and Canada right next to each other. But we really don't have historical examples of countries achieving high levels of living standards without consuming lots of energy. And so number one is energy is critical for growth. Number two is Canada and the U.S. were there. We also have countries down at the bottom who are consuming a lot less energy. And energy access really is a major problem in many parts of the world. So I meant to include Canada, and I failed to do that here. But you'll get the point here. So the average per capita electricity consumption in the United States is about 13,000 kilowatt hours per year. And the U.S. has about 300 million people. In Germany, you could think of it as being about 7,000. But what's really striking is when you go down this, as you move to some other countries, as you take a look, China is just at 3,700, so a little bit more than a quarter of the U.S. level. India is only home to 1.3 billion people, is only about 800 kilowatt hours. I think this is a year old now, it might be 900. The state of Bihar, it's a state in India, it's got a population of 100 million people. Per capita electricity consumption there is 122 kilowatt hours per year. I don't think people in a lot of those places are thinking this is the way we want it to be for very long. And so, indeed, energy access is a major problem. And the next fact follows right from that, which is that demand is going to grow rapidly, or is projected to grow rapidly in the world, but it's going to be almost entirely driven by developing countries. And so here, we just have total energy demand or consumption per capita. This is across electricity, power, and transport. And you can see that over the last, and this is per person, over the last 50 years, it's basically been flat in the US. And it was flat for a long time in India and China, and then it really started to turn up as these countries began to enact economic reforms. And if you were then to aggregate up to the world, you can see and project forward, you can see that basically all of the growth that the world is, this is not per capita anymore, but this is total, all the growth that's projected to occur in the world is projected to occur in non-OECD countries. Okay, so how is the world going to meet this growth, this growth? Well, when you go to kind of the standard predictions, they all point to very heavy continued reliance on fossil fuels. And so in this chart, this is from, I think, the IEA. It projects out to 2040. The three bars, the gray bars on the bottom, are coal, oil, and natural gas. And you can see, although there will be projected big growth in renewables, the bulk of energy is still projected to come from these fossil fuels. And that naturally raises questions about why that is. We hear about, something strange happened to this figure. We hear about lots of improvements in renewables. And I'm sorry, this figure didn't come through quite the way it should. But what you should take away from this is the cost of producing a kilowatt hour of electricity from different sources. And what's striking about it is how inexpensive the fossil fuels are. And so at the bottom, you have an existing coal plant. It can probably produce a kilowatt hour of electricity for maybe 4 or 5 cents a kilowatt hour. A new natural gas plant is maybe 5 or 6 cents. A new coal plant with strict environmental rules, meeting strict environmental rules would be a little bit higher. And then you get into the low carbon technologies. And they tend to be quite expensive relative to the fossil fuels. And that helps explain why the projections are that we're going to continue to use fossil fuels. So that was in power. So I'll be very curious to get Steve's reaction to this figure. Here we try to take a look at, well, what's going to happen in transportation? And what we've done is, on the x-axis there's the cost of batteries projected in 2020. And then there's the price of oil in 2020. And the red line is the break-even point for an internal combustion engine car versus an electric vehicle. And so in the area above the red line, electric vehicles are cheaper, and in the area below, the internal combustion engine cars are cheaper. And so then we just put a few points on this line. And so if you take the DOE, the Department of Energy estimated current price of battery, that I suspect Steve's not going to agree with this, that it's $325 per kilowatt hour. That what would the price of oil need to be to make driving an electric vehicle versus internal combustion engine equal cost over the lifetime of the car, and that would require the price of a barrel of oil to be $420. That's about 10 times the current price. And you can see as you move down, presumably we will move down as there are advances in batteries. Even at a price of a battery of $125 per kilowatt hour, we would need oil prices to be in the range of 115, which is maybe 3 times. This is in U.S. dollars, 3 times current prices. So the point of all this is, even if you set aside things like range anxiety, we got a ways to go with electric vehicles. But again, Steve will know much more about this than me. It's also worth noting that it's not just that fossil fuels are inexpensive, but there's like a lot of them. And it's not just that there's a lot of them, it's that the guys, the men and women who run the fossil fuel companies are very, very good at finding more and more of them. And so this is plotting fossil fuel reserves to production ratios. So reserves are things that we know how to get at today's prices, and then production ratios, how much got produced in that year. And so you would think, if there were no innovation in finding new fossil fuels, that these lines would decline over time. And you can ignore, I think it's probably best to ignore the coal one, because there's more coal than we'll ever use. But take a look at oil and natural gas. Those lines are not declining over time, rather they're flat or maybe slightly increasing. And the reason is that we're finding new oil and new natural gas that's inexpensive to access at a rate that is at least as high as the rate that the world is using it. So the idea that we're about to run out of fossil fuels, it is true in some existential sense, like, over thousands and thousands of years, eventually one could get all the fossil fuels out of the planet, but with respect to economically accessible ones, there's not a lot of evidence using the historical record that we're soon going to run out of fossil fuels. Okay, so that's kind of background. There's going to be energy growth, fossil fuels are cheap, and there's a lot of them. So why is that, why are we focused on that? Well, fossil fuels increase pollution, and that pollution shortens lives. And so let me talk a little bit about a recent paper of mine, which takes advantage of a quirk in policy that existed in China. So China, back in the planning period, did not have enough money to provide heating for everyone. And so what did they do? They said, well, we probably have enough money to heat maybe part of the country. And so they kind of did something that was a little arbitrary, but probably good for research, is that they drew a line across the middle of the country and said, if you live to the north of this line, you get free coal for winter heating. And not just that, we're going to build, little boilers all over the place to provide heat for you. And that'll just be between November and March. And then in addition, if you live to the south of the line, actually you're not allowed to have winter heating. And so that line turned out to be along the Huai River, and then it extends a little into a mountain range in the west. And it is true in recent years, as the market economy has taken hold, heating has started to emerge in the south, but it is still, the legacy of this policy still exists. And so here's an example of a city in the north. So these are just some apartment buildings. These are the little boilers. You can see these are not big centralized boilers that we have certainly in Canada and the United States. These are little ones with no real environmental controls on them and great sources of pollution. So here's our line, and again, that's the Huai River. It's worth noting, like just to drive home the point, in Chengdu, which is a city in the northern part of the south, the winters are actually pretty cold. I gave a lecture there once in the winter in a room not that dissimilar to this. All the students had on winter coats because it's just a deal. There's no indoor winter heating. So the idea of this paper was, well, maybe we can take advantage of that to learn about, well, what are the health consequences of exposure to air pollution? And the idea of the paper is, can we compare places just to the north to places that are just to the south? And this, as I said, I really do like figures. And so here's a figure. And to my eye, it has at least as much beauty as that great picture of the guy on the bike. And what we've done here is the vertical line is right here at 0 is the Huai River. And then plot it for 1 degree at a time going north and 1 degree at a time going south, the level, in this case, levels of air pollution. And then the size of the circles is proportional to the number of people who live there. And what you can see, it's kind of amazing. Again, data is very, very disappointing in general. But here's the settings where the data really kind of are trying to say something very clearly. And that is, as you move just to the north of the line, levels of air pollution go up, and they go up maybe by 50%. And that for those of you who are into pollution, like I am, it goes up by 43 micrograms per cubic meter of PM10. And that's really an enormous difference. I bet you outside right now it's maybe 7 or 8, maybe 7 to 10 micrograms per cubic meter. So this is an enormous difference. And it's not that the south isn't polluted, but it's much more polluted right across the line. So what did I want to do then? the next step was, well, what does that mean for people's life expectancies? And so I'm going to make a graph that looks just like this, and I want to see if there's like the mirror image. And when I did that, what emerged from the data was exactly this mirror image. And so the people who were the intended beneficiary of this policy tend to live about 3.5 or 4 years less than people who live to the south. And we looked and looked, and we were unable to find anything else that changes discretely at the river's border. And I think what it highlights is that my own view is that the greatest current environmental threat that the world faces is air pollution, and that air pollution, the worst version of that is airborne particulate matter. And what this graph aims to just highlight, it's using PM2.5, which is smaller particles, this is a pervasive problem in many parts of the world. So if we go back to that second leg of the stool, there are many, many parts of the world where people are leading shorter and sicker lives due to the exposure to high levels of pollution from the combustion of fossil fuels. Okay, so the sixth fact is that this is kind of like it's called a garbage can fact in the sense that it's got a lot of ideas in it, and so I kind of gave it this vague name. Fossil fuels are causing climate change, and the consequences of that are very, very complicated, both economically and politically and socially, and I'll try and touch upon some of them. So just to give you a sense of what we think might be coming, and this is, so it looks like the graph got shifted again, but just to give you a sense of what's coming, what's projected to come, these are the average number of days that the typical Indian faces where temperature is in these ranges. So this is all shifted over. So these are the average Indian faces a couple days a year where the temperature is projected to be greater than 97. So that's really, really hot. And by the way, that's the daily average. That's not the high. So that's the average of the high and the low. And you can see, but a typical day, since it shifted, it's a little hard to tell, but it might be in the 70s in India. Now here, I'm going to put the distribution of days, daily temperatures that's projected to prevail at the end of the century under kind of a business as usual scenario. And what you can see is like it's not just, people like to talk about, well, 2 degrees C, 3 degrees C. What that misses is there's a lot of action going on in those really hot days. And that's important because a lot of the bad stuff about climate is at the extremes, not because a day in the middle went up by a couple degrees. And so the typical number of days that a person in India would face where the temperature was going to be greater than 97, since the graph's a little screwed up, I don't remember the exact number, but let's call it, will go up to 10 or 12 days, and then you can see there'll be increases at all these other temperature ranges as well. Okay, so what does that mean for people's well-being? So here I'm going to borrow from ongoing research that I'm doing with a couple of my friends on trying to examine, well, what are the consequences of having all these extra hot days in terms of mortality? And we're going to use historical data to try and take a look at this. And first, we just begin by looking at, well, what happens in the United States when there's a hot day? And the exercise that we're doing here is, let's see if we take a day from the 70 to 74 range and shift it either to different one of these ranges, and at the top we have greater than 95 and 90 to 94. And something happened here in this graph too. I hate to say that Canada uses a different technological system than we do, but the key thing is if you zoom in, like we have here, it does look like indeed there are elevated rates of mortality on hot days and also somewhat elevated rates of mortality on cold days. But now I'm going to do a trick here. I'm going to just expand the y-axis. And when I do that, then it looks like there's no relationship. It looks like a flat line. So you really had to zoom in. And you can see it's because the units changed on the y-axis. But when you zoom in, there's really nothing going on there. But it is the same data. So what am I going to do now? You should have a sense of what I'm going to do. I'm going to bring in data from India. And so that's exactly why I had to make the scale so large here. And what's shocking is that climate change will really have enormous impacts. It's projected to have enormous impacts on mortality rates in India. And so the way to read this is if we swap the day out of the 70, 74 range and put it in the greater than 95 range, the annual mortality rate in India would go up by about, you would read this as about 0.7 of a percentage point. That's just for one extra day. And as I showed you, India is going to get many, many more of those days. So climate change is indeed expected to have large consequences on the way we live in places that are wealthy and can use energy to protect themselves from hot and cold. Those impacts will show up in higher energy bills more than they will in mortality, but they're going to show up everywhere. Okay, so that's just a little flavor of what climate change might bring. I also wanted to just raise the politics, and the politics are global politics are pretty complicated, as I think this figure will illustrate. So if you were to say, well, how much of the greenhouse gases in the atmosphere is, say, the United States responsible for, and then we could just, I clubbed China and India together. It's probably not fair, but it's like 2.6 or 7 billion people. And to date, if you go back from the Industrial Revolution to now, the United States is responsible for about 22%, China and India just 16%, and you can see why there's a lot of resistance in China and India and a lot of other countries to engage in really deep carbon reductions, both because they haven't put that much up there, and then if you think about it on a per capita basis, it looks much worse. And then if you go back and think about the very low levels of energy consumption and how high levels of energy consumption might be very, very beneficial, you can see that there's some reluctance. Now, what is interesting, though, since we know that I showed you that the trends in energy consumption are going to point to enormous increases in developing countries, is that it's not going to be that long until these guys are a much larger share. And that still won't be true on a per capita basis, but the planet really does not care if it's on a per capita basis or not. It only cares about total greenhouse gas emissions. And by the end of the century, the United States will be become a small emitter since the beginning of the Industrial Revolution, and these other countries will account for a lot. Now, that's not to say how we should divide the cuts or who should pay for them, but what it makes clear is that if we're going to reduce the probability of disruptive climate change, a lot of the reductions are going to have to occur in these countries. That doesn't say who's going to pay for them, but just as a pure matter of arithmetic, the countries are going to have to do it. So it is important that Canada passed a carbon tax. It would be wonderful if the United States could look to the north and see how politics can work around some of these issues. But even if the U.S. and Canada engage in large reductions, there will have to be large reductions everywhere else as well. Okay. And then just as a last, my wife also tells me to be more positive when I talk. So just as how much warming is actually out there to be used, the scientists all like to talk about in gigatons of carbon and gigatons of CO2 and all these units that I really don't understand. So what I did instead was say, well, can't we convert the carbon that's in the ground into temperature change? That I can understand that. And so the way if you have a scorecard, you should think, well, we've already baked 1.7 degrees Fahrenheit into the system. That's from what we've emitted since the 1870. If we were to use the fossil fuel proven reserves, so that's coal, oil, and natural gas, we can get today at today's market prices with today's technologies, that's probably another 2.8 degrees. And then there's this extra category that the energy industry uses, which is called resources. We know it's there. We can get it with today's technologies, but it costs more than today's market prices would merit. And there, what you can see is that there's just an enormous, there's basically as much fossil fuels as you could imagine, and that's especially true of coal. And so if you added it all up, there is about 16 degrees of warming available. Again, this is in Fahrenheit, not Celsius. And and as I pointed out, a lot of it is very, very inexpensive to access. And this says nothing about further advances in recovery of fossil fuels. Methane hydrates are another category that we have not really started to use at all commercially, and Japan and other countries are working hard at trying to find ways to get at it inexpensively. So that you would have to add that to this. Okay, so with that background, it's maybe worth just going to figuring, well, what did the Paris Agreement actually do? Again, some gremlin here has gotten in the way, but, wow, this is difficult to read, but here's what you should do. If we had done, if the world had done nothing, we were on a path to go up by about 4.5 degrees Celsius by the end of the century. The scientists recommend 2 degrees. To be on a 2-degree path, the emissions of CO2 would have to look like this. So really, really sharp declines would begin pretty soon, by the way. I think that's not happening. And then somewhere in the middle is what the Paris Agreement did, which maybe brought it down from 4.5 degrees by the end of the century to 3.5 degrees Celsius by the end of the century. So, and of course, there's international agreements without, war as a backup are they are commitments, they're not binding. And this is taking at face value what every country has projected to do. Okay, so that's the challenge. Is it so bleak? I actually don't think it's that bleak. There's pretty easy things that can be done, and some of them are being done here in Canada. So the first thing is energy should be priced at its full social cost. So I showed you those figures, and it looks very, very inexpensive to use fossil fuels. But that's because in those figures I obscured or did not meant that was the private cost of producing it. I didn't say anything about the health costs associated with fossil fuels. I didn't say anything about the climate change costs associated with fossil fuels. So we're going to skip this in the interest of time, and we're going to come to this point I want to make here about how energy prices tend not to reflect the full social cost. So just as a reminder, what we looked at a few minutes ago is that to produce a kilowatt hour of electricity from a natural gas plant, it takes about 5.3 cents. And a conventional coal plant is about 8 cents, and a kind of a modern nuclear reactor is about 10.4 cents. You can see that there are some. This is for a plant that would begin production in 2022. You can see here is the cost of other technologies. And I just want to confess that I've done something that some people will probably find slightly unseemly, but I think it's the right thing to do, which is with respect to wind and solar and hydro, so the water is not available all the time, the sun doesn't shine all the time, and the wind doesn't blow all the time. So what I've done is I've built a natural gas plant that sits aside it, and I just have that plant run when these intermittent technologies don't run. So that drives up the cost relative to without backup. And I think that's fair because these technologies are imposing costs on the rest of the system that even if they don't force them to build a natural gas plant right next to them, someone else is building one so that it can step in and meet it. But the key thing is that the fracking revolution has basically made natural gas the winner. And natural gas is better than coal in terms of carbon content, but if we ignored the social cost, we would just choose natural gas plants. We might want some diversity of supply, but natural gas plants look like a winner. And remember, if you're at 1,000 kilowatt hours per year, are you going to want to choose something that is twice as expensive, or are you going to go for the least expensive thing? Now, here what I've done is I've added the U.S. social cost of carbon to this. And so the gray bar is say, well, you know what, the full cost of these technologies is not just the cost of production, but it's the cost they impose on society, in this case, through causing climate change. And the U.S. government has a set for the regulatory policy that the social cost of carbon, so that is the release of an extra ton of CO2, does about $40 worth of damages. And when you apply that to figure out what the social costs are, you can see that this does lead to increases. It makes coal plants much less competitive. You can see how carbon-intensive coal is there. It goes from 8 cents to 13.8 cents. And you can see the impact of for natural gas. It also raises its price to maybe 8.2 cents. It's noteworthy that even that is not enough to get nuclear in the money. But this would be a kind of a first step into making energy choices based on their full social costs. Now, I spent so much time talking about the natural gas backups because if you did have carbon pricing, these renewable technologies, and the backup was a natural gas plant, you can see that there's actually quite a bit of carbon costs associated with them. And that just reflects all the hours. So like the capacity, I think the numbers for a solar plant is really only running 25% of the time, and a wind turbine is really only running 35% of the time. And so you're getting all these extra carbon costs because you're filling in that time with natural gas plant. Okay. Now, of course, if we had, and we'll come to this, if we had advances in batteries, we wouldn't have to use natural gas as a backup, and that would be an alternative. All right, and the last thing I'll do is, what if we put in the health costs? And we saw those at the beginning. And there you can really see, coal plants are not such a good deal. They look like a great deal if you close your eyes about the social costs. But once you add in the health costs, which are the red bar there, electricity looks really, really expensive when you get it from coal. Natural gas is much cleaner, and that's evident there as well. Okay, so that's one thing that we could do, and that would levelize the playing field. So just because we don't pay attention to the social costs does not mean we are not paying them. We're paying them just in indirect ways, and if you had a system where all this is recognized in prices, it would lead to different. It could lead to very different choices. All right. So the second thing that we could do is we could invest in innovation, and some of that is certainly going on. And indeed, there's been very rapid improvements. And the green one there is in solar, where there's been this remarkable improvement in the levelized cost of solar. There's also been some improvements in wind, although it's a more mature technology. And you've just seen these really dramatic declines. There have also been important declines in lithium-ion batteries that are bringing the cost down. And here's some projections into the future, and that would help a great deal as well. But what we shouldn't lose sight of is that there has also been tremendous innovation in the fossil fuels. This is, I think what they do with hydraulic fracturing is actually kind of remarkable, just in terms of an engineering feat. Okay, we're going to drill down 6,000 feet. We're going to make the drill bit make a 90-degree turn. Then we're going to shoot stuff down that hole enough to open up cracks in the shale. And then we're going to remember to put in sand, because the sand will keep the cracks open long enough to get the fossil fuels out. Like that was not easy. And by the way, we're going to do that, and it's going to reduce prices for everything. It's going to disrupt international relations. It's going to, Vladimir Putin certainly does not love the advent of fracking. The guys in Iran do not love the advent of fracking. And these guys are, they're very, very smart guys, and they're coming up with new ways to get access to the fossil fuels that people know are in the ground all the time. With respect to shale gas resources by country, you can see China. So basically, it's been a North American story so far, but these are what the resources that people believe are laying around in other countries. China has not touched it yet. Argentina really has made almost no progress. Here's Algeria, and then here's the 3 North American countries where there has been some progress. But I expect the shale gas revolution to kind of spread beyond North America in the coming years. I think the history of people leaving $100 bills buried in the ground untouched is a very, very short history, and I expect that will not. It'll be short history in China and other places as well. Of course, the hydraulic fracturing has also unleashed all kinds of increases in supplies of oil, so maybe Russia does like that part. But and you can see the distribution here of some key countries. So the generic point is that there has been a lot of innovation in renewables. We're probably not investing as much as you might think we should in our energy R&D, although there's projected to be some big improvements, doubling from the Department of Energy in the United States, and the mission innovation push that came out of the Paris Agreement. And so that's important, but I think why I wanted to march through the hydraulic fracturing and the fossil fuels is the key thing is the low carbon technologies or the cleaner technologies, they don't just have to get better, they got to get better than the other guy. And the other guy is the fossil fuels, and the fossil fuels keep getting cheaper and cheaper. Okay, of course there's also geoengineering. I think some people don't like to talk about that in polite company. It is possible that might look like a good idea at some point. We're not doing a lot of research into it. There's some research being done into it. There's different versions of that: solar radiation management, carbon dioxide air capture, a couple other are listed here. A lot of what people think about geoengineering, not all, comes from the Mount Pinatubo explosion, which put sulfur dioxide in the atmosphere that floated around for a while and was able to actually reduce global temperatures because it reflected the sun back up. And so that's where some of the ideas for geoengineering come from. Is it really a substitute for mitigation? I think it's probably safe to say it's unproven at scale. It's an idea in many instances. There are concerns about undesirable side effects, jellyfish explosions. And then, if you think agreeing on who's going to cut carbon emissions is complicated, imagine trying to argue about who should set the global temperature. I suspect people in Saudi Arabia have a different view than people in Russia, and I don't know how that would be adjudicated. So even if you could solve the scientific problem, I think the political problem is challenging. Okay, so what can we do? I think there is probably a role for research, as I tried to suggest in 2, but there, I think, are other areas where there's opportunities for good research. One, certainly, which I'm engaged in, is to try and estimate what is the social cost of carbon. So, the social cost of carbon, as I said before, is the monetized damages associated with an incremental increase in carbon emissions in a given year. It certainly includes the changes in agricultural productivity, human health, property damages, value of ecosystem services, and on and on and on. Here's kind of what we know. This comes from the 3 leading models. And on the x-axis, we have the temperature changes in Celsius. And on the y-axis, there's the change in global damages. And this is for the end of the century. And they all kind of have this kind of curvature here, such that, at about 4 degrees or 5 degrees, we're off by a couple percentage points of GDP. Now, I think the history of these were really, really important. We needed a framework to think about this, and people were using, I think, what was known when these were first developed in the 1990s. But I think these 3 lines, which are the basis for the U.S. government social cost of carbon, have kind of been left behind. And by the way, for the Canadian social cost of carbon as well, have been left behind by science. And I think there's a lot of opportunities to try and improve them. My former colleague Bob Pindyke writes about them. The bottom line here is the damage functions used in most climate models are completely made up with no theoretical or empirical foundation. So I actually don't agree with that, but I think there's a kernel of truth in what he is saying, and that there's great opportunities to improve them. I'm involved in a project called the Climate Impact Lab, where we are trying to use historical data, like some of the data I showed you from India, to learn about what the costs of climate change are going to be, using data rather than assumptions and intuition. And as part of that, we would develop a new social cost carbon and provide much more detailed, highly resolved data on what will climate change look like, this is China, in very specific parts of the world. So let me close by returning to our guy on the bike. I think what I see is, I think the global energy challenge really is one of the greatest, if not the greatest, problem facing society in the coming decades. It has these three features, and these three features don't all move in the same direction at once, or very rarely move in the same direction at once. And those features are, we need to find a way to have access to inexpensive and reliable energy for people all over the world, not just in Canada and North America and the EU and a couple other rich places. The second is, how do we do that without having very undesirable health and other problems associated with the consumption and production, primarily of fossil fuels? And the third is, how do we have those first two without unleashing disruptive climate change? And I think that's at the heart of what we have to resolve, and I think there is actually a lot of progress being made. Again, Canada's recent adoption of a carbon tax, I think, will really puts it as a leader in the world, and which is, definitely in the direction of pricing energy in its at its full cost, not just at its private cost. And I think the next several decades will be very exciting as we grapple with these problems. So thank you.